Right now, at this very moment, somewhere in the universe, two stars are spiraling toward each other in a cosmic dance that has lasted millions of years. They're moving through space at speeds we can barely comprehend, yet from our perspective here on Earth, if we could watch them, they would appear almost motionless, frozen in an eternal embrace that will eventually, inevitably, lead to their transformation into something entirely new. Welcome to Sleep About Science. Tonight, wherever you are in the world, whether you're tucked into bed in Tokyo, settling down for an afternoon rest in London, or perhaps listening while the morning sun streams through your window in New York. We're exploring what happens when stars collide, and if you drift off to sleep while listening, that's perfectly wonderful. In fact, I encourage it. There's something beautifully appropriate about falling asleep while contemplating the slow, graceful collisions happening in the depths of space. Before we begin our journey through the cosmos, please make yourself comfortable, pull up those blankets, adjust your pillow, and remember that this is educational content, not medical advice. If you haven't subscribed yet, you might want to, so you never miss these gentle journeys into science. And wherever you're listening from, I'd love to know. Leave a comment telling me what part of our beautiful planet you call home. Now, let me ask you to do something. Close your eyes for just a moment. If you can, picture the night sky, not the night sky you might see from your window, dimmed by city lights and atmospheric haze, but the deep, profound darkness punctuated by countless points of light that our ancestors saw. Each one of those lights is a star, and each star is a sphere of superheated gas, held together by its own gravity, fusing hydrogen into helium in its core, releasing energy that travels sometimes for millions of years before reaching your eyes. Most of these stars live their entire lives in relative solitude, separated from their nearest neighbors by distances so vast that light itself, the fastest thing in the universe, takes years to travel between them. Our own sun, for instance, is about 4.2 light years from its nearest stellar neighbor, Proxima Centauri. That's about 25 trillion miles. If you could travel at the speed of a commercial jet, it would take you about 5 million years to make that journey. But not all stars live such isolated lives. In fact, about half of all the stars we see in the night sky are part of binary systems, two stars orbiting around their common center of mass, locked in a gravitational embrace that can last for billions of years. Some are in triple systems, or even more complex arrangements, and sometimes, very rarely on human timescales, but quite commonly on cosmic ones, these stellar companions come too close to each other. Sometimes they collide. When I say the word collision, you might picture something violent and sudden, two cars crashing on a highway, perhaps, or billiard balls smacking together on a pool table. But stellar collisions are nothing like that. They're slow, graceful, almost ballet-like in their execution. They can take thousands, even millions of years to unfold. From our human perspective, they would appear to happen in extreme slow motion, each moment stretching out across generations. Let's start by understanding what a star really is, because to understand what happens when they collide, we need to understand their nature. A star is essentially a battle between two forces. On one side, you have gravity, pulling all the star's material inward, trying to crush it down to a point. On the other side, you have the pressure from nuclear fusion in the star's core, pushing outward, trying to blow the star apart. A stable star is one where these two forces are perfectly balanced. The star neither collapses nor explodes, it simply burns, steadily converting hydrogen to helium, helium to carbon, and so on, depending on its mass. Our Sun, which seems so constant and unchanging to us, is actually a seething, roiling ball of plasma. Its surface, what we call the photosphere, has a temperature of about 10,000 degrees Fahrenheit. But that's positively chilly compared to its core, where temperatures reach 27 million degrees Fahrenheit. At these temperatures, atoms can't exist as we know them. Electrons are stripped from their nuclei, creating a soup of charged particles called plasma. Now imagine two of these incredible objects approaching each other. As they draw closer, the first thing that happens isn't a collision at all, it's a distortion. Stars aren't solid like planets. They're fluid, gaseous, held in their spherical shape only by their own gravity. As two stars approach each other, their mutual gravitational attraction begins to pull them out of shape. They become elongated, stretch toward each other like cosmic teardrops. This distortion happens gradually at first, almost imperceptibly, but as the stars draw closer, the effect becomes more pronounced. If you could watch this process, and we can, in a way, through computer simulations based on our understanding of physics, you would see the stars begin to look less like spheres and more like eggs, their pointed ends reaching toward each other across the diminishing gap of space. The space between stars isn't truly empty, by the way. Even in the vast voids between stellar systems, there are atoms of hydrogen, tiny dust particles, and streams of charged particles flowing outward from stars, what we call stellar wind. As two stars approach each other, their stellar winds collide first, creating shock waves that heat the thin gas between them to millions of degrees. If you could see in X rays, this collision zone would glow brilliantly, a preview of the spectacular event to come. Let me tell you about a particularly fascinating type of stellar collision, one that involves white dwarfs. A white dwarf is what remains after a star like our Sun exhausts its nuclear fuel. Unable to maintain fusion, the star sheds its outer layers, leaving behind a dense core about the size of Earth, but with a mass comparable to the Sun. A teaspoon of white dwarf material would weigh about 15 tons on Earth. These stellar remnants are incredibly hot when they first form, but they gradually cool over billions of years, eventually becoming dark, cold cinders in space. But sometimes, a white dwarf has a companion star. If that companion is close enough, the white dwarf's intense gravity can actually pull material from its partner, stripping away its outer layers in a process called accretion. The stolen gas doesn't fall directly onto the white dwarf. Instead, it forms a swirling disk around it, called an accretion disk. The material in this disk gradually spirals inward, heating up from friction as it goes, until it finally lands on the white dwarf's surface. Here's where things get interesting. As more and more material accumulates on the white dwarf, its mass increases. But white dwarfs have a maximum mass limit, discovered by the Indian American astrophysicist Subramanian Chandrasekhar. This limit, called the Chandrasekhar limit, is about 1.4 times the mass of our Sun. If a white dwarf exceeds this mass, something extraordinary happens. The white dwarf can no longer support itself against its own gravity. In a matter of seconds, and I mean that literally, just a few seconds, the entire star undergoes a catastrophic collapse and then rebounds in a massive explosion. This is a Type Ia supernova, one of the most energetic events in the universe. The explosion is so bright that it can outshine an entire galaxy for weeks. The star doesn't just explode, it's completely destroyed, its material flung out into space at speeds of thousands of miles per second. These Type Ia supernovae are particularly special to astronomers because they all explode with roughly the same brightness. This makes them what we call standard candles, Mythias, projects we can use to measure distances in the universe. By observing how bright a type Ia supernovae appears from Earth and knowing its actual brightness, we can calculate how far away it is. This technique has helped us discover that the expansion of the universe is actually accelerating, a discovery that won the Nobel Prize in Physics in 2011. But not all stellar collisions involve white dwarfs. Sometimes, two main sequence stars, stars that are still fusing hydrogen in their cores, like our Sun, collide with each other. This can happen in dense stellar environments, like globular clusters, where hundreds of thousands of stars are packed into a relatively small volume of space. In these cosmic cities, stars can pass close enough to each other that their mutual gravity sends them on collision courses. When two main sequence stars collide, the process is both violent and beautiful. As they approach each other, tidal forces, the same forces that cause ocean tides on Earth, but immeasurably stronger, begin to tear the stars apart. Material is pulled from each star, creating long streamers of gas that spiral around the colliding pair. The stars don't simply smash together, they merge, their material mixing together in a cosmic whirlpool. The collision heats the gas to tremendous temperatures, causing it to glow brilliantly. For a brief time, brief on astronomical scales, anyway, the merging stars can shine with the light of millions of suns. But this isn't a destructive process in the way a supernova is. Instead of destroying the stars, the collision creates a new star, one that's more massive than either of its progenitors. This newly formed star is often quite unusual. It might rotate extremely rapidly, spun up by the angular momentum of the collision. It might have an unusual chemical composition, with elements from the cores of the original stars mixed into its outer layers, and it will likely be what astronomers call a blue straggler. Blue stragglers were a mystery to astronomers for many years. In a cluster of stars that all formed at the same time, you'd expect the most massive, bluest stars to have already died, since massive stars burn through their fuel much faster than smaller ones. Yet there they were, more bright blue stars in clusters that should have been too old to contain them. It wasn't until we understood stellar collisions that we realized these stars weren't young at all. They were rejuvenated, given a new lease on life by merging with another star. Let me paint you a picture of what one of these collisions might look like up close. Though, of course, up close is relative when we're talking about objects hundreds of thousands of miles in diameter. As the two stars spiral toward each other, their outer atmospheres begin to merge first. These atmospheres are incredibly tenuous by Earth standards, less dense than the best vacuum we can create in a laboratory, but they extend for thousands of miles beyond what we might consider the star's surface. As these atmospheres merge, they create a common envelope around both stars. From the outside, it might look like a single bloated star with two bright cores. The gas in this envelope is heated by the motion of the stars orbiting within it, causing it to glow with a deep red light. Stellar material flows in complex patterns, creating vast conveyor belts of superheated gas that transport energy from the interior to the surface. The two stellar cores continue to orbit each other within this envelope, but their orbit is decaying. The gas around them creates drag, like trying to run through water, causing them to spiral ever closer together. This process can take thousands of years, with the cores completing millions of orbits before they finally merge. When the cores finally do merge, the event is spectacular. The sudden release of gravitational potential energy, the energy that was stored in the system by having two separate masses, heats the merged core to temperatures far higher than either star could have achieved alone. This can trigger a brief but intense period of nuclear fusion, creating heavy elements that neither star could have produced on its own. The violence of the core merger sends shockwaves rippling through the common envelope. These shockwaves can be powerful enough to eject much of the envelope into space, creating an expanding shell of gas that we might observe centuries later as a planetary nebula, though despite the name, it has nothing to do with planets. What remains after all this drama is a single star, but one with a complex history written in its structure. Its core might be hotter and denser than a normal star of its mass. Its composition might show unusual abundances of certain elements, and it might rotate rapidly, perhaps completing a full rotation in just a few hours, compared to the 27 days it takes our sun to rotate once. These collision products can be quite stable, going on to live for billions of years, or they might be unstable, prone to violent outbursts or rapid mass loss. It all depends on the details of the collision, the masses of the original stars, their compositions, the angle at which they collided, and countless other factors. Now, let's talk about an even more exotic type of stellar collision, one involving neutron stars. Neutron stars are what's left after a massive star, one at least 8 times the mass of our Sun, explodes as a supernova. The explosion blows away the star's outer layers, but the core collapses down to an incredibly dense object just about 12 miles in diameter. To understand just how dense a neutron star is, imagine taking all the mass of our Sun and compressing it down to the size of a city. A sugar cube sized piece of neutron star material would weigh about 100 million tons on Earth. The gravity at the surface of a neutron star is about 200 billion times stronger than Earth's gravity. If you dropped an object from a height of 1 meter above a neutron star's surface, it would hit the surface at about 4.3 million miles per hour. Neutron stars are made almost entirely of neutrons' subatomic particles that, along with protons, make up the nuclei of atoms. Under the incredible pressure inside a neutron star, protons and electrons are crushed together to form neutrons. The result is essentially a giant atomic nucleus 12 miles across. When two neutron stars collide, the event is so violent that it literally shakes the fabric of space and time. As the neutron stars spiral toward each other, they create ripples in space-time called gravitational waves. These waves carry away energy, causing the orbit to decay and the neutron stars to spiral ever closer together. We've actually detected these gravitational waves here on Earth. In 2017, the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected gravitational waves from two neutron stars colliding about 130 million light years away. This was a momentous discovery, the first time we detected both gravitational waves and light from the same event. The collision itself happens incredibly quickly. In the final seconds before merger, the neutron stars are orbiting each other hundreds of times per second. Their surfaces begin to deform, pulled out of shape by tidal forces that would rip apart any normal matter. Then, in less than a second, they collide and merge. The collision creates temperatures of hundreds of billions of degrees, far hotter than the center of any normal star. At these temperatures, protons and neutrons can be created and destroyed freely. The merged object might form a black hole immediately, or it might form a hypermassive neutron star that's temporarily supported by its rapid rotation before collapsing to a black hole milliseconds later. But here's the truly remarkable part. Neutron star collisions are where many of the heavy elements in the universe are created. Elements heavier than iron can't be created by fusion in normal stars. The process actually consumes energy rather than releasing it, but in the extreme conditions of a neutron star collision, a process called rapid neutron capture, or the R process, can create elements all the way up to uranium and beyond. In the milliseconds after the collision, the merged object ejects a small fraction of its mass, perhaps a few percent, into space. This material is incredibly neutron rich and undergoes rapid nuclear reactions as it expands and cools. Within seconds, it has created a whole periodic table's worth of heavy elements. This ejected material glows brilliantly as the newly formed radioactive elements decay, creating what we call a kilonova, unlike a supernova, which is powered by the collapse of a star's core. A kilonova is powered entirely by radioactive decay. It glows with a distinctive red color caused by the heavy elements absorbing blue and green light. The 2017 neutron star collision that LIGO detected produced about 10 Earth masses of gold, along with platinum, uranium, and other heavy elements. Think about that for a moment. The gold in your jewelry, if you're wearing any, was likely created in a neutron star collision billions of years ago, before our solar system even formed. You're wearing stellar collision debris. Let's shift our perspective now and think about stellar collisions on even larger scales. In the centers of galaxies, where stars are packed much more densely than in our cosmic neighborhood, collisions are more common. Near the supermassive black hole at the center of our Milky Way galaxy, stars orbit at incredible speeds, sometimes exceeding 1,000 miles per second. In this extreme environment, stars can be torn apart by tidal forces from the black hole, or they can collide with each other at enormous velocities. These high speed collisions are quite different from the slow spiraling mergers we've been discussing. When two stars collide at thousands of miles per second, they don't have time to merge gently. Instead, they essentially explode on impact, their material heated to billions of degrees and ejected into space. These hypervelocity collisions might help explain some of the unusual stars we observe near galactic centers. Some of these stars are extremely hot and bright, showing signs of recent violent events. Others have unusual orbits that suggest they were involved in close encounters with other stars or with the central black hole. Speaking of black holes, let's talk about what happens when a star collides with one. This isn't exactly a collision in the traditional sense, since a black hole isn't a solid object you can hit. Instead, it's a region of space where gravity is so strong that nothing, not even light, can escape once it crosses the event horizon. When a star approaches a black hole, it experiences increasingly strong tidal forces. Remember, tidal forces arise because gravity is stronger on the side of an object closer to the gravitational source. For a star approaching a black hole, the difference in gravitational pull between the star's near side and far side can become enormous. At a certain distance from the black hole, called the tidal radius, these forces become strong enough to overcome the star's own gravity. The star is literally torn apart in a process called tidal disruption. The material from the disrupted star doesn't immediately fall into the black hole. Instead, it forms an accretion disk, spiraling inward over weeks or months. As this material spirals toward the black hole, friction heats it to millions of degrees, causing it to emit intense radiation. We can detect these tidal disruption events from billions of light years away. They appear as sudden brightening in the centers of distant galaxies, lasting for months before gradually fading as the stellar material is consumed. What's particularly fascinating about tidal disruption events is that they give us a way to study black holes that would otherwise be invisible. Many galaxies have supermassive black holes at their centers, but if there's no material falling into them, they're essentially dark. A tidal disruption event lights up the black hole like a cosmic lighthouse, allowing us to study its properties. Now you might be wondering, could our sun ever collide with another star? The short answer is it's extremely unlikely. The distances between stars in our part of the galaxy are so vast and stellar velocities are so low that stellar collisions are incredibly rare. The Sun has been orbiting the galaxy for 4.6 billion years and has never come close to colliding with another star. But never is a long time, and the universe has ways of bringing stars together. In about 4 billion years, our Milky Way galaxy will collide with the Andromeda galaxy. Don't worry, Tesla collisions aren't like stellar collisions. Galaxies are mostly empty space, so when two galaxies collide, the stars usually pass right by each other without colliding. However, the gravitational disruption of a galaxy collision can send stars on new orbits, potentially bringing them closer together. Computer simulations suggest that during the Milky Way Andromeda collision, there's a small but non zero chance that our sun could be ejected from the merged galaxy entirely, or could have a close encounter with another star. Even if such an encounter happened, it probably wouldn't be a direct collision. More likely, the two stars would pass within a few hundred astronomical units of each other, but still a vast distance, but close enough for their mutual gravity to disrupt the orbits of planets. Such an encounter could send Earth spiraling into the Sun or flying off into interstellar space. But again, the odds of this happening are astronomically small. Let's return to the present and talk about how astronomers actually observe stellar collisions. As you might imagine, catching a stellar collision in the act is extremely difficult. These events are rare, and even when they happen, they unfold over timescales much longer than human lifetimes. So, how do we know so much about them? Part of the answer lies in computer simulations. Using our understanding of physics, gravity, thermodynamics, nuclear physics, and more, we can create detailed computer models of stellar collisions. These simulations can compress millions of years of cosmic evolution into hours or days of computer time, allowing us to watch stellar collisions unfold from beginning to end. These simulations have to account for an enormous range of physics. They need to model gravity on scales from inches to millions of miles. They need to track nuclear reactions happening in microseconds alongside orbital evolution happening over millennia. They need to account for radiation magnetic fields, rotation, and countless other factors. Modern simulations can be incredibly sophisticated. Some use a technique called adaptive mesh refinement, where the simulation automatically increases its resolution in regions where interesting things are happening, like the interface between two colliding stars, while using lower resolution in less active regions. This allows astronomers to capture fine details of the collision without wasting computational resources on empty space. Other simulations use a technique called smoothed particle hydrodynamics, where the star is represented as millions or billions of particles that interact with each other through gravity and pressure forces. Watching one of these simulations is like watching a cosmic ballet, with streams of particles flowing and swirling as the stars merge. But simulations alone aren't enough. We need observations to confirm that our models are correct. This is where stellar archaeology comes in. By studying the products of stellar collisions, blue stragglers, unusual chemical abundances, rapidly rotating stars, we can piece together the history of collision events. For example, astronomers have identified several stars with unusual surface compositions that suggest they've been involved in mergers. These stars show elements on their surfaces that should only exist deep in stellar cores, suggesting that material from the core of one star has been mixed to the surface during a collision. We can also look for the immediate aftermath of stellar collisions. When stars merge, they often eject shells of gas that expand into space. These shells can be detected centuries or millennia after the collision, appearing as glowing nebulae surrounding unusual stars. By studying the composition and velocity of these nebulae, we can learn about the collision that created them. One particularly interesting case is the star V838 Monocerotis, which underwent a dramatic brightening in 2002. At its peak, it was one of the brightest stars in the Milky Way galaxy, about 600,000 times more luminous than our Sun. The brightening was accompanied by the ejection of a shell of material that created a spectacular light echo as it illuminated surrounding dust clouds. Astronomers still debate what caused V838 Mon's outburst, but one leading theory is that it was the result of a stellar merger. Perhaps a main sequence star merged with a companion, or perhaps a star swallowed a giant planet. The event gave us a front row seat to watch the aftermath of a possible stellar collision in real time. Another way we study stellar collisions is through asteroseismology, the study of oscillations in stars. Just as earthquakes let us study Earth's interior, stellar oscillations let us probe the insides of stars. Stars that have undergone mergers often show unusual oscillation patterns that reveal their complex internal structure. These oscillations are incredibly subtle. The star's surface might move in and out by just a few dozen meters, causing tiny changes in the star's brightness. But modern space telescopes like Kepler and TESS can detect these changes, allowing us to essentially take ultrasounds of stars and see the signatures of past collisions. Gravitational wave astronomy has opened up an entirely new way to study stellar collisions. When compact objects like neutron stars or black holes spiral together, they create ripples in spacetime that we can detect here on Earth. These gravitational waves carry information about the masses, spins, and orbits of the colliding objects. The LIGO and Virgo gravitational wave detectors have now detected dozens of these events. Most have been collisions between black holes, but we've also seen neutron star collisions and possibly collisions between neutron stars and black holes. Each detection teaches us something new about these extreme events. What's particularly exciting is that we're now doing what's called multi-messenger astronomy, observing the same event with different types of signals. The 2017 neutron star collision was observed in gravitational waves, gamma rays, X rays, visible light, infrared light, and radio waves. Each type of observation told us something different about the event, from the masses of the neutron stars to the elements created in the collision. As our detection capabilities improve, we'll be able to observe even more stellar collisions. The next generation of gravitational wave detectors will be sensitive enough to detect collisions from much farther away, potentially observing hundreds or thousands of events per year. New telescopes, like the Vera Rubin Observatory, will survey the entire sky every few nights, catching the optical signatures of collisions and mergers. We're also getting better at predicting which stars might collide in the future. By precisely measuring the positions and velocities of stars, we can calculate their future trajectories and identify potential collision candidates. While we won't be around to see these collisions happen, knowing they're coming helps us understand how common these events really are. Let me tell you about one particularly intriguing prediction. The binary star system KIC 98322227 was thought to be on course for a merger around 2022. Astronomers predicted it would create a red nova, a type of stellar explosion caused by a merger that would be visible to the naked eye. Unfortunately, further observations revealed an error in the original calculations, and the merger isn't imminent after all. But the episode showed how close we're getting to being able to predict these cosmic events. The study of stellar collisions has implications beyond just understanding the stars themselves. These events play a crucial role in the chemical evolution of the universe. Every element heavier than hydrogen and helium was created in stars or stellar explosions. Stellar collisions, particularly neutron star mergers, are responsible for creating many of the heaviest elements. This means that stellar collisions have directly influenced the existence of life on Earth. The iron in your blood, the calcium in your bones, the gold in your electronics, all of these were created in stellar furnaces and explosions, with stellar collisions playing a vital role. We are, in a very real sense, made of stellar collision debris. Stellar collisions also influence the evolution of galaxies. In dense stellar environments, like globular clusters or galactic centers, collisions can create unusual populations of stars that affect the cluster's evolution. Blue stragglers, for instance, can provide extra light and heat to a cluster that would otherwise be aging and dimming. The black holes created by some stellar collisions can grow through subsequent mergers, eventually becoming the supermassive black holes we see at the centers of galaxies. These supermassive black holes play a crucial role in galaxy evolution, regulating star formation and driving powerful jets that can influence intergalactic space. As we think about stellar collisions, it's worth contemplating the incredible range of timescales involved. The collision itself might unfold over thousands or millions of years, an eternity by human standards. But the physics governing the collision operates on much shorter timescales. Nuclear reactions happen in nanoseconds. Shock waves propagate in seconds. Gravitational waves oscillate hundreds of times per second. This range of timescales is one of the things that makes stellar collisions so challenging to study. We need to understand physics operating on timescales from nanoseconds to millions of years, on length scales from subatomic to stellar. It's a testament to human ingenuity that we can understand these events at all. There's something profoundly humbling about studying stellar collisions. These are events of unimaginable violence and beauty, playing out on scales that dwarf our everyday experience. Yet we can understand them, predict them, and learn from them. We can look at a star in the night sky and know that it might be the product of a collision that happened billions of years ago. As you drift off to sleep tonight, perhaps you'll dream of these cosmic collisions. Picture two stars, each one a giant sphere of superheated gas, slowly spiraling toward each other through the darkness of space. Watch as they distort, their surfaces stretching toward each other across the narrowing gap. See them merge in a blaze of light and energy, creating something new from their combined substance. Remember that the atoms in your body have been on incredible journeys. They were forged in the hearts of stars, blasted into space by supernovae, enriched by neutron star collisions, and eventually incorporated into the cloud of gas and dust that became our solar system. You are connected to these cosmic events in the most fundamental way possible. The universe is full of violence, the stars exploding, galaxies colliding, black holes devouring matter. But this violence is also creative. It creates new elements, new stars, new possibilities for complexity and life. Stellar collisions are part of this cosmic creativity, transforming and recycling stellar material in ways that make our existence possible. As we continue to study stellar collisions, we'll undoubtedly discover new types of events, new mechanisms, new connections to other cosmic phenomena. Each discovery will add another piece to our understanding of the universe and our place in it. We might discover that stellar collisions are more common than we thought, or that they produce effects we haven't yet imagined. Future space missions will give us unprecedented views of these events. The James Webb Space Telescope can peer through cosmic dust to see the infrared glow of merging stars. The Nancy Grace Roman Space Telescope will survey vast swaths of sky, catching stellar collisions as they happen. Future gravitational wave detectors might be sensitive enough to detect the slow spirals of normal stars, not just compact objects. We might even witness a stellar collision in our own galaxy that's bright enough to see with the naked eye. Imagine walking outside one night to see a new star in the sky, knowing that you're watching two suns becoming one. It would be a reminder of the dynamic, ever changing nature of the cosmos. But for now, in this moment, the universe above us appears peaceful and eternal. The stars shine steadily in their courses, following orbits that have remained stable for billions of years. Yet we know that this is just an illusion created by the shortness of human life compared to cosmic time. The universe is in constant motion, constant change, constant collision, and creation. Stellar collisions remind us that even stars, those symbols of constancy and permanence, are mortal and mutable. They can merge, transform, and create new things. In a universe where even stars can collide and merge, anything seems possible. As you continue to relax, letting your mind wander through these cosmic vistas, remember that you don't need to remember all these details. You don't need to understand every aspect of stellar physics or gravitational wave astronomy. Simply let the wonder of it wash over you. The fact that we live in a universe where such incredible events occur and where creatures like us can discover and understand them. The stars that might be visible outside your window tonight or all on their own journeys through space. Most will never collide with another star, living out their lives in relative isolation before quietly fading away. But some, somewhere, will meet another star and merge in a cosmic embrace that creates new elements, new stars, new possibilities. Each stellar collision is unique, influenced by the masses, compositions, and histories of the stars involved. Some create spectacular explosions visible across the universe. Others proceed quietly, two stars becoming one with little fanfare. Some create black holes, regions where space time itself is twisted beyond recognition. Others create blue stragglers, stars that seem to have found the secret to stellar youth. We've talked about many types of stellar collisions tonight. Main sequence stars merging in globular clusters, white dwarfs exploding as supernovae, neutron stars colliding and creating gold, stars being torn apart by black holes. Each type has its own physics, its own timescales, its own consequences for the universe. But they all share something in common. They're part of the cosmic recycling system that has been operating since the first stars formed over 13 billion years ago. Stars formed from gas clouds, live their lives fusing lighter elements into heavier ones, and then return their enriched material to space through stellar winds, planetary nebulae, supernovae, and, yes, collisions. This recycled material becomes part of new gas clouds, which form new stars with a richer mix of elements. These newer generations of stars can have planets, and those planets can have the complex chemistry needed for life. We are products of this cosmic recycling, beneficiaries of billions of years of stellar evolution and death. As you drift closer to sleep, let your mind float among the stars. Picture yourself witnessing a stellar collision from a safe distance, perhaps from a planet orbiting a nearby star. Watch as two suns spiral together over the course of years, their light gradually changing color as they heat up from the interaction. See the streamers of gas flowing between them, glowing with the colors of heated hydrogen and helium. Watch as they finally merge, brightening dramatically as their combined mass creates higher temperatures and pressures than either star could achieve alone. Observe the shell of gas ejected by the merger, expanding outward like a soap bubble filled with starlight. And then, as the excitement dies down and the merged star settles into its new existence, notice how it's different from before. It's more massive, hotter, rotating faster. It has a future that neither of its progenitors could have had. It's a new thing in the universe, created from the combination of two old things. This is the magic of stellar collisions. They create novelty in a universe that might otherwise wind down into cold uniformity. They're part of the creative force that has taken the simple hydrogen and helium of the early universe and transformed it into the rich complexity we see today. From the gold in the electronics of the device you might be using to listen to this, to the iron in your blood, to the calcium in your bones, you carry the evidence of stellar collisions in every atom of your body. You are intimately connected to these cosmic events, even as they occur in places and times far removed from your daily experience. This connection between the cosmic and the personal, between stellar collisions happening millions of light years away and the atoms in your own body, is one of the most profound insights of modern astronomy. We are not separate from the universe. We are part of it, made of it, connected to it in ways that are both scientifically precise and poetically beautiful. Tonight, as you sleep, Your body will continue its own quiet recycling, breaking down old proteins and building new ones, replacing worn out cells with fresh ones, all using atoms that have been on incredible cosmic journeys. Some of the carbon atoms in your DNA might have been forged in a star that collided with another billions of years ago. Some of the oxygen you're breathing right now might have been created in the final moments of a stellar merger. It's getting late now, wherever you are in the world. Perhaps you're already drifting off, your consciousness beginning to fragment and reform in the strange landscape of dreams. Or perhaps you're still listening, still following along on this journey through the cosmos of colliding stars. Either way is perfectly fine. There's no test at the end of this, no need to remember every detail. Simply let the ideas and images flow through your mind like stellar gas flowing between merging stars, beautifully, naturally, without force or pressure. Let me leave you with one final thought about stellar collisions. In all the violence and drama of these events, the crushing gravity, the searing temperatures, the explosive forces, there's also a kind of cosmic gentleness. Stars that have traveled alone through space for billions of years finally meet and merge, becoming something greater than they were apart. In a universe that can often seem cold and indifferent, stellar collisions remind us that even stars don't always journey alone. Sometimes paths converge. Sometimes separate things become one. Sometimes the universe creates new possibilities through encounters that transform everything they touch. As you settle into sleep, know that you're safe here on Earth, protected by our atmosphere, our magnetic field, and the vast distances that separate us from these cosmic events. You can appreciate the beauty and drama of stellar collisions without fear, wonder at them without worry. The stars will continue their dances, whether we watch them or not. Somewhere in the universe right now, two stars are beginning their final spiral toward each other. Somewhere else, a collision that started when dinosaurs roamed the earth is just reaching its climax. And somewhere else still, the products of an ancient collision are providing the raw materials for new planets, perhaps even new life. Thank you for joining me on this journey through the cosmos of colliding stars. Thank you for your time, your attention, and your curiosity. Whether you're drifting off to sleep or still listening, I hope you found some wonder in these cosmic events. If you enjoyed this gentle exploration of science, please consider subscribing so you never miss an episode. And I'd love to know where in the world you're listening from mine. Leave a comment and tell me about your corner of our beautiful planet. Until next time, this has been Sleep About Science. Sweet dreams, and may your sleep be as peaceful as the space between the stars, and your dreams as spectacular as when those stars collide. Good night.